Hello everybody. So in this video we'll start talking about the first law that was put to describe the mass transfer by diffusion, and this law was produced or made by a scientist whose name was Adolf Fick, who's this guy here. And he has already suggested a definition for the molar flux, which he gave a symbol of J. It's relative to the average velocity, which is a really important point, and we will be discussing this in more details in the next video. But he did, or his law was valid under the isothermal and isobaric conditions, meaning that the pressure and temperature between the 2 points where mass transfer is taking place is constant, so it's the same temperature, the same pressure. And again, we will talk about this in few minutes, why it's valid only for isothermal and isobaric conditions. And this law is called Fick's law because it's named after Adolf Fick, so it's why it has this name. And this law is or states that the flux is directly proportional to the gradient of the concentration gradient, and this is the proportionality constant, which is the diffusion coefficient, which is and this law is very similar to the law of conduction, which states that Q equals negative K, which is the thermal conductivity, and here we have the diffusion coefficient or the diffusivity, and this is the gradient of concentration, and in heat transfer it's gradient of temperature. So it's almost the same law with the corresponding terms in mass transfer. And here we have the term D is the diffusivity of A and B, and it represents, or it kind of tells how fast or slow the diffusion process is. So if it is a fast diffusion process, then the diffusion coefficient is going to be a high value, or it will have a high value, and vice versa. And for this symbol might be new to some of the audiences. So this inverted triangle, it's not delta, it's called nabla or del. And del C or nabla C is the gradient of C with respect to the three coordinates or space coordinates. So let's say we are using the Cartesian coordinates, then we have the three parameters or space parameters are x, y, and z. So in this case, the gradient of concentration is the partial Ca partial x plus partial Ca partial y plus partial Ca partial z. So these are the three components of the concentration gradient: one in x direction, one in y direction, and one in z direction. And here we have three independent variables. So the concentration depends on x, and it depends on y and z, and that's why we have these are like partial differential equations, because we have more than one parameter affecting the concentration. If we have more than one parameter, or if we have only one parameter, let's say it only is function of x, and we don't have y and z, it's going to be dc by dx. In this case, it's an ordinary differential equation. No, since we have more than one independent variable, it's a partial differential equation. So it has partial c partial x plus partial c partial y plus partial c partial z. And there might be a question is why we have negative sign here, and this is the same case for heat transfer like here. So the mass transfer is taking place from point 1 to point 2, so the distance is increasing as we go from point 1 to point 2, and as the distance increasing, the concentration decreases because we are moving from the high concentration to low concentration, or the fusion takes place from high concentration to low concentration. So as the delta x increases, delta c decreases. So this term is negative. This is a negative term, so we put a negative sign here to make this whole flux positive value. So this is why we have it, and this law is called Fick's first law. It's not just Fick's law, because there is another law that we will see later. It's called Fick's second law, and Fick's first law is what we call it, and to differentiate between first law and second law. And the diffusion that obeys the Fick's law is called Fickian diffusion. This is a common name. If you see flow that's called Fickian diffusion, it means that it follows the Fick's law. Anyway, so again, if we have the diffusion only in one direction, so if it's not changing in y and x direction, it's only changing in z direction, then again, as I mentioned before, this is gonna be dc by dz. And the again, J is the molar flux, and we mentioned earlier that the J, if it's uppercase, then it's molar. If it's lowercase, then it's mass. So this is the molar flux in z direction. And again, this is an important point to notice, that this is the flux relative to the molar average velocity. So it's not the absolute flux, it's the flux relative to the molar average velocity. Again, dc by dz is the concentration gradient in z direction. dAB is the mass diffusivity or diffusion coefficient of component A diffusing through component B. And again, this is going to be one point which is different between mass and heat transfer. So in heat transfer, you just mentioned that this material, I know the heat is transferring, let's say, through steel, through copper, whatever the material that the heat is transferring in, and then you put just the thermal conductivity of this material and it's done. But in this case, we have the diffusion coefficient is function of the diffusing species and the medium that this species is diffusing in. So you will always find the diffusion coefficient containing two species in the subscript. You will have A and B, which AB means A diffusing in B, and it's going to be different if you have A diffusing in C or D or E, another medium, or you have another species diffusing in B. So this is an important point, which makes the prediction and the calculation of or estimating the value of the diffusion coefficient very tricky, and it's not a straightforward process because there are a lot of variables included here. And this is something that we will discuss in details in the rest of this chapter, inshallah. And now let's go back to the previous slide here, just to see or revisit this part. Why did we say that this is valid only for isothermal and isobaric conditions? The reason is that this equation, from what we see here, it states that the concentration is dependent on x, on y, and on z. So it's function of the three parameters that we see here. As we know, the concentration is the number of moles per unit volume. So if the volume changes, the concentration will change. So if I have a case where the temperature is changing or the pressure is changing, especially if it is in the gas phase, then these two parameters will affect the concentration, because the increase in the pressure will make the concentration higher, because it's affecting the volume, and the same for the temperature. If the temperature increases, then the volume increases, then the concentration will increase. So this makes the equation not accurate, because if it takes into account all the parameters that affect the concentration, then I should see a parameter here that is similar to these, that contains partial Ca, partial T, and another parameter that contains partial Ca, partial T, one for pressure and one for temperature. This is not what we see here, and that's why we claim that or we say that this equation is valid only for isothermal and isobaric conditions, because I consider that there is no effect on the volume or on the concentration consequently due to any change in temperature or pressure, because it's not included in the parameters that we have here. So if I have a case where the pressure or the temperature change, then I have to do some changes to the equation. So either, as I mentioned, to put some new terms to take into account the pressure and temperature effect, or to use a gradient of concentration. We already used many types of concentration units, or we know many types of concentration units, so we can shift to another unit that is not a function of the pressure or temperature, which is the mole fraction. So if I think about mole fraction is the number of moles of the species A divided by the total number of moles. It has nothing, it's not affected by the pressure or the temperature, and that's why it's gonna be a good alternative if I want to use it. And this is what I would do. I would again use the diffusion coefficient and multiply it by the concentration gradient. I have a negative sign, but I am multiplying it by the overall density or concentration, assuming that this I can find an average value which represents the whole system or the whole area or the whole volume where the mass transfer is taking place. So here the concentration gradient is dya by dz, and it's multiplied by the diffusivity. But again, I have to make sure that the units are consistent and everything is equal from the right hand side and left hand side. So I multiply this by the concentration to make the units homogeneous. And the same here for the mass units, it's the lowercase j, and I multiply the diffusion coefficient by the density of the mixture, and then again this is the overall or the average density of the mixture, and then multiply it by the gradient with respect to the gradient of the mole fraction with respect to z direction. So this is the general equation for molecular diffusion. Again, this can be applied for isothermal, non-isothermal, and non-isobaric conditions. And it was proposed by D. Groot. I don't think it's famous as Fick's law is famous, maybe because Fick is the first person who did this, and then D. Groot just did some modification to the equation, so that's why it's not as famous as Fick's or as Fick from the mass diffusion or the mass transfer point of view. Anyway, so this equation is a general equation, and it can be applied for isothermal and isobaric conditions, and in such cases then the C and rho will be constant because they are not variable from point 1 to point 2, because it's the average and there is no difference. So in this case we can put them inside as a constant into the differentiation, and then this will end up to be the Fick's law again. This is for mass, and this is again applied for molten mass, and it works. So this is the equation that we have. Now then there is an important question that we need to think of, which is why do we have the molar flux, or why we say that Fick's law is used to calculate the molar flux relative to the average flux. Or with relative to the average flux. I'm sorry, and I'm not saying it's only the molar flux. Why do I say this part of the text? This is kind of a question that will jump into your mind, and this is a very legitimate question, and we will answer it in the next video. So I'll see you then.